Okay, let's start with our notes. I cannot discuss your redox homework yet because some of you have not submitted. So we are going to go with these notes. So if you have these notes, please take it out now. And in the meantime, I will send you something. Oops. Okay, I sent it. These pages I actually took from what's this called? No. Is it free exam paper? Save my exams, okay, because it's very good explanation and it's enough for us. So let's first finish off this part. Yeah. So we finished with page 5 last time. Now page 6. We all know the definition of strong acid and strong base. Okay, they are acids and bases that dissociate completely in water. So because they dissociate completely in water, there is a high concentration of H3O plus ions, or what we normally say H plus ions is the same thing, and OH minus ions in the solution, right? So to express complete dissociation, we also use this one-sided arrow, not the reversible arrows. And examples of strong acids and bases are these following. Now for weak acid and bases, they only undergo partial dissociations in water, so we use the reversible arrow. And because they only partially dissociate, there is very low concentration of H3O plus and OH minus or OH minus in water. Okay. By by partial dissociation, I'm not talking about 40% or 50%. I'm talking about 1 over 10 to the power of 5 fraction. So it's that small. So this is saying that if you have 100,000 molecules, only one dissociates. That's how weak acids and bases are actually what they actually are. All right. Nitric acid is considered a strong acid, even though the dissociation is actually only 40%, if I'm not mistaken. It's not even 100%, but we just say, okay, this is strong enough. Okay, so that's why we always assume it's 100% dissociation for nitric acid also. Okay, so let's talk about HCl. If HCl is partially dissociated, it will become H plus or Cl, NCl minus. Okay, or we can also write it like this: H2O plus HCl gives H3O plus and Cl minus. They're the same thing. Now, my question is, HCl is obviously the acid, and it is a strong acid. Okay. Now, which one is the conjugate base? Maya, what is the conjugate base? Yep, which is, in this example, is HCl is the acid. So what's the conjugate base? Conjugate base will show up on this side. Which one is the conjugate base? Is chloride. Yes, so this is the conjugate base. Now, the acid is super strong. Okay, super strong. Meaning this HCl really want to go that way. Really want to go that way, to the right. Okay. Now, this conjugate base, what about it? Does it want to go to the left side at all? No, it doesn't want. All right. So this conjugate base is a super weak base. Right? Very, very weak base. So if the acid is a very, very strong acid, the base becomes a very, very weak base, because this chloride ion doesn't want to go in the reverse direction. That's why the arrow is pointing only to one side, not reversible. Okay, so if I have do another example. I'll do sodium. Okay, it has nothing to do with acid base, but it's the same context. Sodium is a very, well, I'll do one more better example. Francium, right? Francium is the most reactive metal. So it will steal any possible chance to become Fr plus and release one electron. Now, so this is a very, very reactive metal. All right. Now, what happens to francium ion once it is formed? Does it want to gain this electron back and form francium metal again? No, right? Because this arrow lies heavily, if not completely, to the right, right? This francium ion does not want to go back to the reverse direction because it's already stable. So here, if you start with a very, very reactive metal, the result of the ionization will be very, very unreactive or very, very stable ion. Okay, so the reactivity and the unreactivity is opposite. The more reactive the metal, the more stable the ion. Is similar to acid. The stronger the acid, the weaker the conjugate base. Because a strong acid means it doesn't want the H plus. So once it loses the H plus, whatever conjugate base is formed doesn't want the H plus back. Okay? Right. So, similar with weak acid and bases, we have weak ethanoic acid, right? So because we start with a weak acid, meaning this ethanoic acid does not want to lose H plus. It's holding on for dear life to the H plus ions, right? It doesn't want to give it to someone else, right? So it's making the ethanoic acid actually a weak acid because it's holding on to H plus. It loves the H plus. So once, let's say, by force, this H plus ion is taken away by water, would the ethanoate ion, would it like to have the H plus back? Yes, because CH3COOH loves the H plus. So that makes ethanoate ion a strong conjugate base, which means this is likely to gain the H plus ion. Okay? Similar with ammonia. Ammonia is a weak alkali. Meaning what? Meaning it really doesn't want to interact with water and release OH minus, right? Or it does not want to gain H plus. That's how we describe bases, right? Bases are proton acceptor. So a weak base means it doesn't really want to gain a proton, even though it's possible to gain, but it really doesn't want. All right. So here, once it is forced to gain a proton, it will readily lose the proton back to the conjugate acid. So this makes ammonium ion a strong conjugate acid because it readily donates the H plus. Okay. So what do we learn from here? We learned that the weaker the acid, the stronger its conjugate base, and vice versa. Question? Okay. Now, when we do titration, maybe you have seen this before. We sometimes need to plot pH over volume of titrant, a graph, right? From the graph, you can actually predict. If we don't really do the practical ourselves and we just look at the pH titration curve like this, we can actually predict if this titration is between strong acid, strong base, or weak acid, strong base, or strong acid, weak base, or whatever. All right, we can predict from the shape of pH titration curve. This is important for two reasons. So if you have the curve, you can predict at what volume, right, the acid is completely neutralized. Because if you do only titration and you do not plot this pH titration curve, you always overshoot. All right. For example, methyl orange. You go from yellow in the alkaline region, and then you titrate with acid, 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 and then it becomes orange, right? But at orange, pH is already around 4. You cannot stop at pH 7. So it's always going to overshoot by a little bit at least, all right? But if you plot the curve, then you can really see, oh, at what volume exactly the titrant neutralized the acid completely. Okay? Now, that's the first one. The second thing is we can exactly know where is the optimum buffer region. But buffer I will explain in another time. So for today, I'll just explain how you draw a titration curve. Of course, you can do the actual practical, which means you take, let's say, strong acid, all right, strong acid, and then add strong base, and also plot the pH every time you add half a mil or something, half a cm cube of titrant. All right, so you plot pH over volume of titrant used. So pH you measure using pH meter. Okay, but in the exam, written exam, you are not doing the titration yourself. So this is how you do it. If you have strong acid and strong base titration, all right, the strength of the acid and base will cancel each other. So if the strength of acid and base cancel each other, pH must be 7 when they neutralize each other. Okay, so this neutralization is called the equivalence point. Equivalence point is where the concentration of the H plus from the acid is equal to the concentration of OH minus added in the titrant. Okay, that is the equivalence point. This is where neutralization happens. This is where the equivalence point of strong acid, strong base lies. All right. Now, because let's say you start with, in the beaker, you start with strong acid, right? And here you start with a strong base. So your pH meter will measure this first. All right, this is the pH meter, the pH probe. Is electronic thing. Okay, so you will start with pH around 1 for a strong acid. For a weak acid, the pH will be around 3. But for strong acid, it could be pH 1. Sometimes pH 0, doesn't matter. we will not be too picky. As long as you use 1 or 0, it's fine. Okay, just use 1, guys, for strong acid. And then as you add your strong base, okay, the pH change by very, very little bit. It changes, but very little. Okay, so this should be a little bit inclined towards up like that, but not much. Now at this point here, just before the vertical shoot up, at this point, imagine that in your what's this called, conical flask, all right, in your conical flask you only have a few more H plus, all right, because you already neutralize most of the H plus. Okay, and then each of the titrant drop that is added here, now this titrant is a strong alkali, so each drop will contain high concentration of OH minus. All right, let's say it contains 50 particles of OH minus. All right, so you only have 3 particles of H plus left, but you are adding 50 OH minus particles, so only 3 of these will be needed to neutralize the remaining H plus, right? So what is the other 47 OH minus do? These other 47 will raise the pH significantly. So that is what happens here. That's why it shoots up really drastically. This is because the few remaining H plus ions in the conical flask is gone and now is replaced by excess OH minus from that 1 drop of strong alkali. Okay, and after that, this pH is just going to be almost stagnant at 13. This is around 13, pH 13, if you use strong alkali. Okay, so that's what you need to be aware of. First, the starting pH is 1 for strong acid. The pH of the equivalence point is 7 for strong and strong titration, strong acid, strong alkali. And the final pH is around 13 if you use strong alkali, right? So 1, 2, 3 points that you need to know. Question? Okay. I will continue this in the class, so thank you for joining me tonight, and I will see you tomorrow. Bye-bye.